Dear students, welcome to our YouTube channel ChemOrigin. This is Dr.Satish Kumar. Students, in this video module, we discuss about the theories of coordination compounds. Theories of coordination compounds. So students, there are some popular theories which explain the formation of a complex compound. So what are those two theories and what are the postulates in the theories? What are the advantages of the theories? What are the drawbacks which are present in the theory? We can discuss it detailedly in this video module. Now students, we can start our class. Dear students, in the theories of coordination compounds, we can discuss about some theories which explains the formation of complex compounds. So students, there are some theories which explains the formation of coordination compounds or formation of complex compounds, how the complex compounds may formed or detailedly explained by some theories. In that theories, the popular one are Werner's theory, Sidgwick theory, valency bond theory. These are some theories to explain for the formation of a coordination compounds or the formation of a complex compounds. So students, out of these three theories, now we can discuss about the Werner's theory. Werner's theory. What are the important postulates in Werner's theory? What are the advantages of Werner's theory? What are the defects in Werner's theory? We can detailedly discuss it now. Students, the postulates of Werner's theory. Postulates of Werner's theory. Students, a complex compound, according to Werner's theory, a complex compound has always a central metal atom. This may be an ion or a neutral atom. So students, according to Werner's theory, a complex compound always contains a central metal atom. It may be an ion or a neutral atom. This is the first postulate for Werner's theory. And the second one is a metal. A metal in a complex compound has two types of valencies. So students, in the complex compound, the metal has two types of valencies according to Werner's theory. Those are primary valency and secondary valency. So students, for a complex compound have the central metal have two types of valencies, primary valency and secondary valency. And the postulate number 3, primary valency means the oxidation state of the metal atom or the ion in the complex compound. So students, primary valency is nothing but the oxidation state of the metal atom or ion in the complex compound. Similarly students, the secondary valency is nothing but the coordination number of the central metal. Coordination number of the central metal is the secondary valency. Students, primary valency is also known as a ionizable valency. Secondary valency is also known as a non-ionizable valency. So students, you should remember primary valency. According to Werner's theory, central metal has a two types of valencies. Those are primary valency and secondary valency. Primary valency is also known as a ionizable valency and secondary valency is also known as a non-ionizable valency. Primary valency is equals to the is nothing but the oxidation state of the central metal atom or the ion, and the secondary valency is nothing but the coordination number of the central metal. Coordination number of the central metal is the secondary valency of a complex compound. Next, fourth postulate. Students, in a complex compound, according to Werner's theory, every metal has a fixed number of secondary valencies, or that is nothing but coordination number in each of its oxidation states. So students, every metal has a fixed number of secondary valencies, that is nothing but fixed number of coordination number in each of its oxidation states. This is the fourth postulate of Werner's theory. And the fifth postulate is the coordination number. The coordination number of the metal is the number of ligands. The coordination number of the metal is the number of ligands, which gives the number of coordinate covalent bonds formed with the central metal atom or ion in a complex compound. So students, according to Werner's theory, the coordination number is nothing but the ligands which can form a coordinate covalent bond with the central metal atom or an ion in a complex compound. Similarly, students, generally majority of complex compounds have a coordination number 2 or 4 or 6. So generally students, the complex compounds which exist with the coordination number either 2 or 4 or 6, which are the common coordination numbers for a complex compounds, that is 2 or 4 or 6. For example, students, if you take cobalt 3 complex compounds or platinum 4 complex compounds, generally cobalt 3 complex compounds or platinum 4 complex compounds have 6 coordination number. Its coordination number is 6. For example, students, if you take hexamine cobalt 3 chloride, CONH3 6Cl3. So students, in this example, there are 6 NH3 ligands. There are 6 amine ligands directly connected with the central metal cobalt. Therefore, in this complex, the cobalts, the central metal, the coordination number is 6. Here the central metal is cobalt and its oxidation state is 3. Similarly, students, if you take one more example, that is potassium hexachloroplatinate 2, K2PtCl6, K2PtCl6. Students, in this example, 6 chlorine ligands are directly form a coordinate bond with the central metal platinum, and in this complex the oxidation state of platinum is 4. So in K2PtCl6 complex, the coordination number is 6. The coordination number is 6 because here 6 chlorine atoms can form a coordinate bond with the metal platinum, and here the oxidation state of platinum is 4. Therefore students, in generally cobalt 3 complex compounds, platinum 4 complex compounds can form a coordination number 6. Similarly students, copper 2 complex compounds, platinum 2 complex compounds, zinc 2 complex compounds or coordination compounds generally can have a coordination number 4. For example, if you take CuNH3 4 2 plus CuOH4 2 minus PtNH3 4 plus 2 ZnCN4 minus 2. So in all these examples, the coordination number is 4 only. So students, in the first example, 4 NH3, 4 amine ligands is form a coordinate bond with the copper. Similarly, in the second example, 4 OH minus ligands can form a coordinate bond with copper metal. In case of PtNH3 4 plus 2, 4 amine ligands can form a coordinate bond with platinum. In case of ZnCN4 minus 2, here 4 CN ligands can directly connected with the central metal zinc. So in this way, copper 2, platinum 2, zinc 2 complexes can have generally coordination number 4. If you take students silver 1 complex generally can have a coordination number 2. For example, if you take AgNH3 twice plus, AgNH3 twice plus, diamine silver 1 cation. Similarly, if you take AgCN2 minus, dicyno silver, dicyno AgCN twice minus. So here in this example, two amine ligands are directly bonded with the silver. In case of AgCN twice, two cyanide ligands are directly coordinate bond with the central metal silver. So here the coordination number is 2 only. Coordination number is 2. Students, postulate number 6. The secondary valencies of the central metal is satisfied either by negative ions or by neutral molecules or by positive ions. So students, in a complex compounds, the secondary valencies of the central metal is satisfied by negative ions. For example, Cl minus, Br minus, Cn minus, or by neutral molecules. For example, H2O, NH3 are the examples for neutral molecules which satisfies the secondary valencies of the central metal, or by positive ions like NH2, NH3 plus or NO plus. So the secondary valencies of the central metal is satisfied either by negative ions or by positive ions or the neutral molecules. Students, there are some complex compounds. There are some complex compounds which can exist in which both the primary valency as well as the secondary valency satisfied by negative ions. So there are some complex compounds which exist in which both primary valency and the secondary valency satisfied by negative ions. For example, students, if you take CONH34Cl2 Cl, in this complex both primary valency and the secondary valency are satisfied by the negative ions. Satisfied by the negative ions. Next, postulate number 7. The primary valency. The primary valency is satisfied by negative ions. So students, generally in complex compounds, the primary valency is satisfied by negative ions. Next, the ligands. The ligands are directed in space around the central atom symmetrically in such a way that the complex has a definite structure. So students, the geometry of the complex compound, the shape of the coordination compound, the shape of the complex compound is decided by the ligands. How these ligands is arranged spatially around the central metal determines the structure of the complex compound or geometry of the complex compound or shape of the complex compound. So students, how the ligands are arranged around the central metal atom in space determines the geometry of the complex compound. For example, students, if you take complex compound, if a complex compound have two ligands, in generally the complex compound which has two ligands have a shape or geometry linear geometry, linear structure. For example, students, AgNH3 twice plus, AgNH3 twice plus. So this complex has a linear geometry. In this, the central metal is attached to two ligands. So the complex compounds generally which have two ligands can form a linear geometry or linear shape or linear structure. For example, students, if the complex compound has a four ligands, it may form the structure tetrahedral or square planar. So the complex has a four ligands. It has either tetrahedral geometry or square planar geometry. For example, students, if you take NiCO4. So students, in this complex, the geometry of the complex is tetrahedral geometry. Whereas in case of NiCN4 2 minus, the shape of the complex or the structure of the complex or the geometry of the complex is square planar geometry. Next, suppose students, if the complex compound has a 6 ligands, it has a octahedral geometry or octahedral shape. For example, students, CONH363 plus. In this complex, the central metal cobalt is arranged around the space 6 NH3 ligands in a octahedral geometry or octahedral shape. So students, the complex compounds which have a 6 ligands generally can form a octahedral geometry, whereas the complex compounds which have a 4 ligands can form a either tetrahedral geometry or square planar geometry, or if the complex compound have a 2 ligands which are generally can form a linear structure or linear geometry. So students, based on the Werner's theory, the complex compounds geometry we can discuss it. Next, postulate number 9. The charge of the complex ion. The charge of the complex ion is equal to the sum of the charges of metal and ligands. The charge of the complex ion is equal to the sum of the charges of metal and ligands. For example, students, if you take K4FeCN6, K4FeCN6, in this complex, the oxidation state of the central metal iron is +2 and the oxidation state of the ligand Cn minus cyanide ligand is -1. Therefore, the charge of the complex ion is 2 plus 6 into -1, that equals to -4. Therefore, -4 is the charge of the complex ion. That is nothing but FeCN6 4 minus. FeCN6 4 minus. Therefore, the charge of the complex ion is equal to the sum of the charges of metal and ligands. Sum of the charges of metal and ligands is the charge of the complex ion. This is postulate number 9. Students, now we can see what are the advantages of Werner's theory. Werner's theory, students, Werner's theory can explain the isomerism in complex compound. For example, students, if you take CONH34NO2 2 plus, it has two geometrical isomers. For example, if you see in the first complex, which is a cis 1, it is a cis 1, whereas in the second isomer, it is a trans 1. It is a trans isomer. Cis isomer, trans isomer. In case of cis isomer, the two NO2 ligands are adjacent to each other. The two NO2 ligands are adjacent to each other. Whereas in case of trans complex, the two similar NO2 ligands are opposite to each other. Trans isomer, which are adjacent to each other, cis isomer. So students, Werner's theory can explain the isomerism in complex compounds. Next, advantage. Students, we can distinguish the complex compounds which are having same molecular formula. The complex compounds which have the same molecular formula, we can differentiate with the help of Werner's theory. For example, students, if you take CONH35SO4Br and the same molecular formula, another complex is CONH35BrSO4. So students, these two complexes we can distinguish easily, because students, if you treat the complex one, that is CONH35SO4Br with a silver nitrate AgNO3, it can form yellow precipitate, because students, whenever if we treat the CONH35SO4Br with AgNO3, it can produce us here silver bromide, AgBr. Silver bromide will be formed, AgBr. It have a yellow precipitate. Whereas students, if you treat the complex 2, that is nothing but CONH35BrSO4 with the barium chloride solution, it readily gives the white precipitate. The formation of white precipitate in this reaction is because of the formation of barium sulfate, BaSO4 will be formed. So students, here the complex 1 and complex 2 both are having same molecular formula. One CO central metal, 5 NH3 ligands, one bromine ligand, one SO4 ligand. Even though both these complexes are having same molecular formula, but which can give different reactions. So complex 1 is treated with silver nitrate solution, it give a yellow precipitate. Whereas the complex 2 is treated with barium chloride, it can produce as white precipitate because of formation of BaSO4, barium sulfate solution. Students, defects in Werner's theory. So students, just now we discussed the advantages of Werner's theory. There are some defects in Werner's theory. So what are those? We can see. Werner's theory does not correlate electronic configuration of the central metal with the formation of a complex compounds. Because students, now we know that the central metal is try to acquire the next inert gas structure through the coordinate bond formation. Then hence complexes are formed. So students, the central metal try to acquire the next inert gas structure through or via coordinate bond formation. That's why the complexes are formed. But according to Werner's theory, which does not correlate electronic configuration of the central metal with the formation of the complex compound. This is the first defect in Werner's theory. And another defect in Werner's theory is the postulates of Werner's theory does not explain the color property of the complex compounds. Does not explain the color of the complex compounds. Students, in general, the complex compounds or the coordination compounds exhibit color due to D to D transition takes place, due to the electron transition from d orbital to d orbital, which is known as a d to d transition, that d to d transition, how it will takes place is not explained by Werner's theory. So whenever it is unable to explain the d to d transition, so it does not explain the color of the complex compound, it does not explain the color property of the complex compound. This is the another drawback of the Werner's theory. Next drawback. So students, Werner's theory is incapable of explaining the magnetic behavior. The magnetic behavior of the complex compounds are not explained by Werner's theory. So students, Werner's theory is unable to explain the magnetic nature or magnetic behavior of the complex compounds. Because students, we know that the magnetic property in general, the magnetic property is depends upon the number of unpaired electrons, present in the metal ion, but here in the Werner's theory there is not related to electronic configuration, and so this property could not be explained by Werner's theory. So students, these are the defects in Werner's theory. So students, Werner's theory does not correlate the electronic configuration of the central metal. It does not explain the color property of the complex compounds, and it also unable to explain the magnetic nature or magnetic behavior of the complex compounds. So students, these are the postulates, advantage and defects in the Werner's theory. Okay students, I hope you enjoyed this session. Students, in this video module we discussed detailedly about the Werner's theory for the formation of a coordination compounds or complex compounds. Thank you students, thank you very much.